Organizers of this workshop for the invitation, to the organizers of the whole program. It's really great. Could only visit during the 3 workshops, but it's been really really great. And thank you all for staying until the very end. Maybe we should have, like in these big Maybells, these parties that they organize at Cambridge colleges at the end of the year, they have the survivors picture at 6 a.m., something like that, people that made it to the end of the party. Maybe we should have one at the end of this session. So, okay, so we are all a bit tired. So this is going to be about orthogonal polynomials with a bit of a complex analysis flavor. So kind of non-standard orthogonal polynomials and a bit of computational aspects, many questions, not too many answers. But okay, hopefully interesting also because of the motivation behind this. So, okay, Friday afternoon, I guess that I was a bit late in the week, so I guess this standard theory of orthogonal polynomials has appeared one way or the other at some point. This is the very, very plain vanilla theory of orthogonal polynomials. There are many classical references where you can go for more details. If you have a positive weight function, you can do this with measure theory, but okay, again, it's Friday, so weight function on an interval of the real line, this we are going to change later on, such that the moment, so this integral of any polynomial with respect to the weight function is finite. Then if this happens, then you can construct a family of monic orthogonal polynomials, and this is just Gram-Schmidt orthogonalization of the canonical basis with respect to L2 inner product with this weight. And then you get some polynomials Pn that are orthogonal in this sense. This inner product is 0 against any polynomial of lower degree, and some constant, positive constant Hn if the degrees are the same. This is the L2 norm of the polynomial, essentially. Pn exists uniquely. You can choose your normalization. We are going to take monic orthogonal polynomials, but there are other options. And, okay, this being a computational workshop, in principle, you can compute this using Gram-Schmidt, but it's not very recommended. Okay. Talking about not very useful computational things, maybe, there's an alternative formulation that is a very nice result, but again, with big and lots of big determinants, so maybe not the best idea either. If you construct a Hankel determinant, so you put the moments of your weight function in a matrix with Hankel structure, so constant along antidiagonals, and then you border it with an extra column and then powers here, then this is a polynomial of degree n if you divide by dn, and you can check that this is indeed the same, the nth monic orthogonal polynomial with respect to the weight function that gave rise to these moments. So this is, again, computationally, this is not very useful if you want to compute the polynomials. The important thing here is that it gives a criterion for existence of this family of orthogonal polynomials. Basically, if you know how this Hankel determinant behaves, you know that all the minors, principal minors, are different from 0, are non-singular, then Pn exists, and you are in business. In other words, if you start doing strange things with your weight function, which is what we're going to do, and dn becomes 0, then, well, the whole thing breaks down, in principle. Okay. Classical cases of orthogonal polynomials, well, we know these are the 3 classical families on the real line with the weight, the Gaussian, the gamma distribution, the beta distribution, the whole line, half line, and finite interval, and with restrictions on the parameters. This is just so that the moments exist. Okay. So these are the classical cases. Of course, people have looked at many different families. But one technique, one idea that seems to be quite fruitful is to consider certain, I'm going to be very vague here, certain deformations of the classical weights. So over and over again, you find examples in the literature, which is, okay, this is a classical weight and some deformation. And this exponential here makes sense because you keep the weight being positive, so things are likely to stay in place with this new weight function. You can deform, this is deformation of Laguerre. You can put something singular here, okay. There's a cubic weight here. This is not classical, but okay, you see the same kind of deformation with a parameter. This is a deformation of Laguerre, Hermite, depends how you want to look at it. This is half line, but this is a quadratic exponential. And the list goes on and on. It just gets more and more complicated. You can put more parameters. You can put another singularity into the weight. This is a modification of Jacobi again. You can modify Jacobi with an even extra singularity outside the interval of orthogonality, and so on and so forth. So there are many examples in the in the literature. But if you look at it, I mean, my impression is that this similar kind of deformations over and over again. And there are reasons for that, is that, well, basically you go into the area of integrable systems from this perspective, and then there are lots of things that you can say if your deformation is of a certain type. So I'll discuss this a bit in a moment. So why orthogonal polynomials? Well, this is a bit embarrassing here, but first, okay, the construction of Gaussian quadrature rules. So the first thing that one learns in any decent course of numerical analysis when you get to numerical integration. So if you have this weighted integral, then this quadrature rule maximizes the degree of exactness, so the degree of any polynomial that you integrate exactly, if and only if the polynomial, well, you're using as nodes the zeros of the nth orthogonal polynomial with respect to this function w. And then you have, well, you have the classical rules, Gauss-Hermite, Gauss-Laguerre, Gauss-Jacobi, and then many variants. And in principle, if you can compute your orthogonal polynomials and you can compute the zeros, then you have a rule for whatever family of orthogonal polynomials you are working with. This is a bit of a variation on this. So oscillatory integrals, this actually is a very nice thing to discuss here, because this started in this, the program in 2007 on highly oscillatory problems. So there has been a lot of work on highly oscillatory integrals and highly oscillatory differential equations. And the message that comes over and over again is that if you try Gaussian quadrature, great as it is, directly on this type of integrals, then this is not efficient, it's not reliable, because the number of sampling points that you need in order to get any kind of decent accuracy basically scales with the frequency. So if omega is very large, then this is basically useless. One alternative that I guess has been mentioned here several times this week is to do a steepest descent analytically or numerically, deform into the complex plane, and transform this high oscillation into exponential decay. So here's an example with a cubic weight with parameter, okay, between 0 and 1. And then basically what you do in this case, you deform from -1 to infinity in a certain direction in the complex plane where things decay with the exponential decays, back through the stationary points and then back to 1. And then, well, what you would do is consider these 4 contour integrals instead of the integral on the real line. You parameterize, and then you use a standard, or more or less standard Gaussian quadrature rule. Gauss-Laguerre and Gauss-Hermite, basically. Gauss-Laguerre for the endpoints, Gauss-Hermite for the stationary points. Now, the idea that, that we explored is that not so standard approach, just glue these 2 paths together and try to come up with one quadrature rule that deals, or tries to deal, with the whole contour in one go. So now you have a contour on the complex plane, and you have a weight function that is not positive, so it's not even real valued. So what happens in this situation? Well, you can say, okay, formally, I have the same construction, and then we'll pretend that this works. So I impose the same orthogonality condition. Now my weight is complex. Fine. And then, okay, I rescale the parameter with omega, so now it is the parameter delta. There is another point of view of these orthogonal polynomials. They can be used in random matrix theory, just as a side note. So it's a kind of cubic log-gas model, if you know what that means. Now the question is, okay, this weight is not positive, so what about the orthogonal polynomials? Do they exist or not? Well, depends. It boils down basically to study the Hankel determinant. So you have this Hankel determinant, you construct the moments are very simple. These are incomplete gamma functions, actually. And then you try to, the game is, okay, try to determine when this Hankel determinant is different from 0. So there are quite a few things that you can say asymptotically, when n tends to infinity, for example, when delta tends to infinity, when you couple the two parameters. What is actually quite hard is to say anything for finite n. That still remains, looks like a silly problem, but it's actually a bit complicated. So if you want more details about this motivation, there are several papers together with people in Leuven, Dan Heubrechts, who unfortunately had to leave earlier today, and many more details, of course, in the book that we wrote with Ari that I had to advertise some way. So this is one motivation, that you start playing with this steepest descent approach to highly oscillatory integrals, and then you want to be efficient when you integrate that numerically. So that leads you, in principle, it's not the only option, but is a certain optimal choice with Gaussian quadrature. But then you need this complex variant that it's a bit intriguing. You can do calculations. Things exist. For example, these polynomials exist for even degree. We don't know how to prove it for finite n. And that's motivation number one. Motivation number two has to do more with probably the other two workshops in this program. Has to do with solution of Painlevé differential equations. If you have been around here, probably Peter has given more than one talk on this. So very briefly, because time constraint, Painlevé differential equations are nonlinear differential equations whose solutions are sometimes called nonlinear special functions, so a kind of nonlinear version of special functions. Painlevé 2 has appeared here several times in relation with the Hastings-MacLeod solution that you need, that you can do via Riemann-Hilbert. But here I'm interested in certain families of solutions, so this is a slightly different situation. You have this nonlinear differential equation, but you can construct families of solutions in terms of linear classical special functions, and these are called special function solutions. And these solutions have a very nice structure, or can be constructed from Wronskian determinants, where D is typically the derivative, but it could be something a bit more complicated, and you put here a seed function that is a classical special function. So for example, in Painlevé 2, alpha equal to 0, that was that's where the Hastings-MacLeod solution appears, but in this case you have a parameter here that is actually half an integer. And then you have airy solutions, and they can be constructed from this Wronskian determinants, where this phi function is general solution of airy differential equation with two constants C1 and C2. And then there are several Painlevé differential equations, 6 in total, and for 5 of them you have this similar construction with different classical special functions. And then, so what does this have to do with complex orthogonal polynomials? Well, it's an interesting idea here, is that if you want to study these solutions, then you can try to reverse what you did before. So before you start with the weight function, you compute the moments, you go to the Hankel determinant. Here you have a Wronskian determinant of this kind. This is a special function, classical special function. So here's an idea: look for an integral representation of this, real or complex integral, and then try to match this, the entries in this Wronskian determinant, with a Hankel or Toeplitz structure. And if you manage to do that, then you have to cook up a suitable weight function and a suitable contour so that the moments match the derivatives of the seed function. But if you can do that, then basically you have your special function solution of Painlevé written in terms of quantities that have to do with complex orthogonal polynomials in general, with some other weight. So this has been explored for other families of solutions of Painlevé, like rational solutions, a bit of special function solutions of P2 that I did last year. And then, well, this can be done in general for finite n. You can do asymptotics from here as well. Once you are in the game of orthogonal polynomials, even in the complex plane, then Riemann-Hilbert, if you manage to, the steepest descent, if you manage to make everything work, then you get asymptotic information of this solution. So there is another source of strange complex orthogonal polynomials. The last motivation is random matrix theory. Again, crash course on this. Again, back to the Hankel determinant. We don't want to compute anything with the Hankel determinant, but it's a very, very useful object because this Heines formula, which basically allows you to rewrite a determinant whose entries are these moments, these integrals of powers times the weight function, as a multiple integral, or the other way around. The interesting thing is that this, immediately, if you've done a bit of Hermitian random matrix ensembles, you recognize this essentially as the partition function of a random matrix ensemble. So you have a Hermitian random matrix whose eigenvalues, real eigenvalues, are you label x1 to xn, and then, well, basically this tells you how to normalize the probability law on this ensemble of random matrices, and this is essentially the partition function. So this game you can play with Hermitian random matrices and then with orthogonal polynomials on the real line. More recent material that I worked with, together with Nick Sim, it's on the archive, it was recently on the archive. You can play this game with non-Hermitian random matrix ensemble. So you keep this, you keep similar structure of your random matrix ensemble, but you lift the Hermitian condition. So now the eigenvalues will be complex, and then you deal, instead of with orthogonal polynomials on the real line, with orthogonal polynomials in the complex plane. And then, well, things here are a bit different, but you can modify this, and again you end up with non-standard families of orthogonal polynomials in the complex plane, again with non-positive weights. So what happens there? So briefly, this is three possible sources of these orthogonal polynomials. There are many more places where orthogonal polynomials are useful. You can complete the list if you want. Approximation theory, Padé approximas, rational approximation uses orthogonal polynomials, typically in the complex plane as well. Spectral methods for differential equations and whatnot. Right. So if you want to, well, you try to compute things, orthogonal polynomials or related quantities, one very useful identity that is, again, very elementary when you start working on orthogonal polynomials is the three-term recurrence relation. So Pn minus 1, Pn plus 1 are related by a linear difference equation, and this is just a consequence of orthogonality. So you have this kind of relation with some coefficients beta n, sorry, this should be beta n, not beta n of x. Beta n is a constant. You have two initial values. You can write this in matrix form, and then, well, you basically have here a tridiagonal Jacobi matrix or Jacobi operator if you consider the infinite case. Right, so you can, well, if you want the orthogonal polynomials, you just, well, you can do computation with this three-term recurrence relation, provided that you have the recurrence coefficients. So the recurrence coefficients are typically not easy to compute in the non-classical families of orthogonal polynomials. And then there are several possible approaches, well, directly to nodes and weights in Gaussian quadrature. There are recent work of many people in the audience, actually. If you want to compute recurrence coefficients, there's the standard reference is the book of Gauci, where he discusses, from a numerical point of view, several methods, starting from moments of the weight function. That's not a very good idea. Modified moments is a bit better. And if you want Gaussian nodes and weights, then, well, you have all the tools from linear algebra the moment you write the orthogonal polynomials as this in this form, because then the zeros will become eigenvalues of the Jacobi matrix, and the quadrature weights are related to the eigenvectors. So then you can use method of Golov-Welsch, which is basically an eigenvalue eigenvector calculation. So this is if you want to compute the recurrence coefficients. Once you have the recurrence coefficients, you can work out the orthogonal polynomials in principle. The thing is that this is a bit intriguing, and actually I don't know if it's a real alternative, but there is something going on here. Is that you can write this three-term recurrence relation and other identities for orthogonal polynomials in a way that is very much in the language of integrable systems. So what I mean by that is that instead of considering just your polynomial, then construct this vector, and I guess several people will recognize this as the first column of a 2x2 Riemann-Hilbert matrix for orthogonal polynomials. And then what you can do, you can say, well, this Pn satisfies two linear systems. This vector I can write, so Pn plus 1, some matrix times Pn. This is essentially the three-term recurrence relation written in matrix form. And if I differentiate, then I have Pn prime, and then this is a bit harder to work out, but there's another matrix times Pn. And this is rational, in general, rational matrix, this Pn. And then you say, well, okay, then compatibility. If I do Pn plus 1 prime from here or from here, then I have to arrive at the same thing. And this compatibility condition looks like this, and this is sometimes called compatibility, zero curvature condition, and it's essentially a Lax pair. This is essentially a Lax pair formulation of the orthogonal polynomials. So you have a structure here that maybe you can take advantage of, also for computations. If you have extra parameters, then you have a third player here. You can consider the derivative with respect to parameter. And then, well, you have another matrix times Pn, and now you have the three players here. And then you can start playing compatibility. And here's, okay, this is anything but precise, but typically if you combine the identities in x in n, the derivative and the shift, you get what is called string equations, Freud equations, depend where you read it. And these sometimes are related to discrete Painlevé, depending on the deformation, on the type of weight that you have. This is not a theorem, but in many cases that I've shown before, if you play this game, then you arrive at some discrete Painlevé equation, which is a discrete integrable system, actually. If you play with t and n, then you have some kind of evolution equation. And again, if you have an exponential deformation, chances are that you will end up with very well-known evolution systems, like the total lattice, Langmuir, Ablovitz-Ladek, in the unit circle, and so on. And if you play t and x, then you, in some cases, you will arrive at the continuous Painlevé equation. So there's a whole structure here that I think puts the orthogonal polynomials, even in the complex case, into a very nice framework. Question is that if this helps in any way to compute recurrence coefficients, for example. So there are very well-known examples in the cubic weight that I had before with this highly oscillatory integrals. If you do the compatibility, the first one, the n and the x, I think, you get the string equations, these string equations. There's a paper of people in Leuven, actually two papers. And then with these initial values are prescribed by the zero moment, so that you're integrating between two sectors in the complex plane. Actually, if you eliminate one of the recurrence coefficients, then you get an equation in one of them, actually, and this is a discrete Painlevé equation, as you can see in the paper of Peter, Ana Logredo, and Walter Van Asse. And they prove that if you have this kind of nonlinear recurrence relation, this is nonlinear, they prove that there is a unique solution for which Bn of delta is positive. And this is the one that you want for the recurrence coefficient. So in general, the solution could be anything, but this is the one that you want. And it's clear that you're asking for trouble if you try just iteration of this to try to catch this precise solution. And indeed, that's what happens. So there are very well-known experiments. If you try to plot the recurrence coefficients, this should tend, so this asymptotic behavior is very well known. And then, well, this experiment with Maple, you increase the number of digits, but eventually it will blow up. This is the location of the zeros of the orthogonal polynomial, by the way. And these are the recurrence coefficients that eventually, well, it will give garbage here. This is for delta equals to 1. You change delta, then the configuration of the zeros can change, and you can even go to a two-cut case where you have zeros distributed on two different arcs. Well, this looks like it's working, but if you continue, even with 60 digits, sooner or later, it will blow up. So this is just, thank you. This is just, well, this is just naive experimentation with this nonlinear difference equation. And you have many other examples. If you want, there's the recent book of Walter, where he discusses many other cases of non-standard orthogonal polynomials where the recurrence coefficients satisfy this kind of nonlinear identities, and typically the calculation is a disaster as an initial value problem. There are more complicated cases where when parameters appear as discontinuities of the weight function. So instead of a nice parameter in an exponential, you put the parameter, for example, v as a singularity of your weight, or s as a jump parameter. And then you can play the formation here, and things kind of work, but the identities are considerably more complicated. You're still, if you are careful, you're still in the Painlevé world, but things can become a bit trickier. So related problems, questions kind of open. This instability is it related to the choice of special functions as initial values? So you have this nonlinear difference equation, you have initial values that are prescribed from, well, if you're doing a Gaussian quadrature, but you need a contour where things are well defined, that prescribes the initial value. These initial values are classical special functions, and classical special functions satisfy linear recurrence relation, and it's well known that there are minimal solutions in the linear case, and if you try forward calculation for a minimal solution, it's a disaster. This looks vaguely similar in a nonlinear context. Is it related? I don't know. Possibly a better idea, boundary value problem. Instead of running the discrete equation as an initial value problem, then take an initial value and take the behavior at infinity, if you know the behavior at infinity, and compute in between. That has been done in the literature. There's a paper of Liu and Carls. But it can be tricky because the condition at infinity is typically asymptotic, so it's not convergent. So you know that goes like, for example, the recurrence coefficient goes like a power of n, but there are more terms, and this is divergent. So where do you prescribe the condition at infinity and how many terms you take? Another intriguing question that Blair and Nitz, who are not numerical analysts, but in a paper in 2003, they proposed, and there's a little numerical experiment, minimization of this Hamiltonian. So you have a weight function in this form. V is a polynomial. So you take this function of infinitely many variables, so a vector of gammas and a vector of betas. This is a Hamiltonian. And then they claim, okay, if you minimize this, they prove if you minimize this Hamiltonian, then that minimizer corresponds to the recurrence coefficients for the orthogonal polynomials with respect to this. And this works nice. And they put a plot, and it works for this quartic case. There's another possibility. And again, it's the language of Hamiltonian, etc., Hamiltonian functions. And again, well, we've seen Fredholm determinant techniques. There's a paper of work of Bornemann, at least for solutions of Painlevé, for example, that have to do with random matrix theory. But you have to be able to write Fredholm determinant with a kernel that you can control in order to discretize and compute the way he does. Yet another possibility, Riemann-Hilbert problem for orthogonal polynomials, and the numerical solution, like she and Tom proposed 4 other examples related to Painlevé and PDEs. But this is very much a combination of ideas that I think brings together some elements from integrable systems that not sure how to use them, and some techniques that have been discussed here. So very much work in progress, or any ideas will be welcome. And I think I'm done. Thank you very much.
Questions, comments?
Yeah.
Do you know if there are synchronics for large n?
Mm-hmm.
Is it factorially divergent, or is it superfactorially, or what?
Which one for the?
You mentioned that it's divergent for large n.
For example, in the
Recurrence, the W and the polynomial expression as you iterate in n for large n, you mentioned that you start with S, but it's at infinity.
yeah. So
So do you know how it is divergent? You know the leading order.
yeah, in this case, the leading order is, for example, in this case, is a power. I think this is power n to 2/3 or n to 1/3, depending on which recurrence coefficient.
It's divergent. So how is the divergence happening?
Yeah, so you start. So this is asymptotic to n to power 1/3, for example, plus corrections.
Yeah.
But this series is not convergent. So for
Do
an
you know how it is divergent? Because there is still the Borel summation.
Okay, yeah, that I haven't. Okay, yeah, that I haven't explored. No, but it's probably okay. No, there's definitely.
In the interest of time, I think we should
Yeah.
continue this discussion later.
Later.
So let us now go to the final topic.
Thank you. Should I close this?